Assalamualaikum. Today our group will be presenting about experimentally which is maneuvering test. Our group consists of Muhammad Sahil, Muhammad Arishak, Muhammad Afi Hakim, Muhammad Amir Hakim and one Azim Akif. Okay, next is overview. This presentation includes introduction, objective, methodology, results, discussion and conclusion. For the next slide, which is introduction. So, what is a tension lift platform? TLP. A tension lift platform is a floating offshore structure used for deep water oil and gas production. It is anchored to the seabed using vertical tension lifts that provide high responsiveness and excellent stability. So, why is this experiment important? It evaluates the hydrodynamic behavior of the offshore structure. It also studies the response under different current velocities. It measures 6 degrees of freedom motion. It also assesses the stability of performance of TLP during towing. Now we move on to the next slide, which is objective. The objective of the experiment is to investigate the motion response of the TLP model under different towing speed. The next objective is to analyze the 6 degree freedom motion, which is surge, sway, heave, roll, pitch and yaw. And next is to determine the motion amplitude from the experiment data. Next one is to calculate root mean square RMS values, examine the influence of tow speed on the platform behavior, and lastly is to identify the critical towing speed associated with the largest motion response.
So for the experimental setup, the testing facilities are the indoor towing tank. We use 5 towing speed, which is 0.15 until 0.35. The equipment we use is quasi motion tracking system, Duotron DAQ system, compression spring system, air bearing system, towing carriage, and lastly, computer and control software. So the experimental procedure is the model preparation. Install the 1 to 70 TLP model in the towing tank, and then we connect the spring restraint system, and then calibrate the quasi motion tracking system and Duotron DAQ. So while the testing process, we set the towing carriage to the required speed, which is 0.15 until 0.35. We record all the 6 DOF motions during each run. And lastly, the data processing. We export the motion data from the quali-size and DAQ system, determine maximum, minimum, and mean values, and then we calculate motion amplitude and root mean square error. And lastly, we plot graphs for comparison and analysis.
Next, we move on to the next slide, which is result. There are 5 different tow speed, which is 15, 20, 25, 30 and 35. The result we get from the experiment is surge amplitude, sway amplitude, heave amplitude, roll amplitude, pitch amplitude and lastly yaw amplitude. This is the data we get from the experiment. Key observation: surge produce the largest translational motion. Sway increased significantly at 0.35 meter per second. Heave remained comparatively small throughout the experiment.
So for this slide, we have 4 things to discuss, which is surge motion, pitch and yaw behavior, vortex-induced motion, and overall trend. So for surge motion, we need to dominant motion throughout the experiment and increase with towing speed due to higher drag forces. For pitch and yaw behavior, pitch was the dominant rotational motion and yaw increased significantly at 0.35 due to asymmetric hydrodynamic forces. Next, for VIM, sway motion remained low at lower speed. So they increased sharply at 0.35, indicating stronger vortex shedding effects. So for the overall trend, increased tow speed result in greater hydrodynamic loading and larger platform motions. So for the recommendation, we need to improve the TLP performance, which is install vortex suppression device, or we can increase the tendon stiffness for better stability. And then other choice, we need to optimize hull geometry to reduce sway and yaw motion, conduct FFT, and lastly, validate the experimental result using CFD simulation. In conclusion, the objective of the experiment was successfully achieved. Surge was the dominant translation motion, pitch was the largest rotational motion. So for the VIM become more significant at 0.35 meter per second. The spring restraint system effectively limited heave and roll motions. And lastly, higher towing speed produced stronger hydrodynamic forces and greater motion responses.